So once again, let's focus on this exact same example of trying to predict prime numbers, the next prime with linear regression. So X is going to be 1, 2, 3, 4, 5, just like always here so far. And Y is going to be the prime numbers 2, 3, 5, 7, 11. Again, don't try this at home. This is not the way you want to get. This is not something you want to apply linear regression to, but we're doing it just for fun and illustration. And I'll show you the things I showed you at the end of class the other day here, just to remind you of them. It is nice to find the sum of these columns with equals sum, like this. Copy and paste that over to add the y's as well. It's nice to find the means. I should say sums. Means with, say, just equals average, or I could divide each of those other numbers by 5. Standard deviations, STDEV. Don't add on a P there, by the way, because that would be a population standard deviation, a sigma. No, we never ever use sigma from data. These are our sample standard deviations. I haven't really said what a correlation coefficient is with data, but we're using it anyway. It's supposed to measure the strength of the linear regression. Highlight the first list, highlight the second list there. It's close to 1, meaning it's a pretty strong linear regression. It's a pretty strong linear trend for these 5 data points. Actually, the squared correlation is a better measure of the strength of a linear regression. The squared correlation. It's called the coefficient of determination, but you don't need to know that. So I could square this correlation. It's still pretty close to 1. It's still a pretty strong linear trend. When R squared is close to 0.5, that's sort of the prototypical moderately strong linear trend. If R squared is close to 1, it's a very strong linear trend. If it's close to 0, it's not much of a linear trend at all. Anyway, the slope and the intercept can be found. The formula that I use for the slope here is one you do not need to know for the exam, but I'm showing to you anyway. Take R times standard deviation of the y's divided by the standard deviation of the x's. You can use the formula in the book involving the summations. That's something you should be able to do for the test. And the intercept, this is a formula you should know. This is the one in the book. Take the mean of the y's, y bar, subtract the slope you just found, times the mean of the x's. Y bar minus B1 times X bar. Find B1 first. Find the slope first, then find the intercept, -1. By the way, the fact that B0 is Y bar minus B1 times X bar, the fact that that's how you find the intercept is equivalent to saying Y bar is B0 plus B1 times X bar. In other words, the point whose coordinates are the mean of X and the mean of Y is always on the regression line. Therefore, this point X bar comma Y bar is on the regression line. Always. Doesn't mean it's a data point, right? Usually it's not a data point. It would be a very rare thing for X bar comma Y bar to be an actual data point. But that point whose coordinates are those means is always on the regression line. One thing I didn't have time to emphasize on Tuesday was that the formula for the regression line in our book is written in 2 ways. One way is as y hat equals B0 plus B1x. And another way is as mu sub y given x is B0 plus B1x. Right? You read about that, came up on the homework. Both ways of writing the equation of the regression line are valid, are fine. Why do we have two different ways of writing it? The 2 different ways of writing it emphasize the 2 different uses of the regression line. When we write it this way, we're emphasizing that we use the regression line to predict or estimate a value of y when we know x. When we write it this way, we emphasize the fact that when we use the regression line, we can think of it as being used to predict the mean of the y's when we know x. Both applications of the regression line equation are valid. It's a little bit more valid, or maybe a little bit more robust, you might say, to use it to predict the mean. A little less robust to predict an individual value, because there's more variation in the individual values in the y direction. Just pretend you got a lot of data points, a big cloud of data, maybe thousands of data points, and you got a regression line going through the middle. You're going to be able to get a line that predicts the mean of the y's in any given value of x more easily than an individual value of y, because there's lots of spread in individual values of y. So it's probably better to think of it in terms of using it to predict the mean. But either way is a valid use. Before we look at the regression output that you should be able to read for the exam, let's show some work that emphasizes that the formulas in the book also work here. I'm going to make a column for values of x squared, values of y squared, values of x times y. This is worth doing to re-emphasize some things here. How do I figure out the values of x squared? Take the values of x and square them, right? 1 squared is 1, 2 squared is 4, etc. Why'd that happen? Go. 5 squared, for example, is 25. I can copy and paste that whole column over here to get the values of y squared, because I didn't use any dollar signs to fix the cell references. Yep, for example, 11 squared is 121. Can't copy and paste here. I need equals b2 times c2. X times y, 1 times 2 is 2. Why'd that go away? Didn't do anything. There we go. Copy and paste that downward. And for example, doing it again. I think it's my mouse pad. For example, 55 is 5 times 11. If you think about the regression formulas for the slope in the book, it's going to be useful to sum up these numbers as well. So I copied and pasted the sum formula over to these spots. Let's think about the formula for the slope that's in the book. All right, you see the slope, which we're trying to put into this row here, is a ratio, use parentheses, n, 5, right, there's 5 data points, times the sum of x times y, which is in F8, minus the sum of the x's times the sum of the y's, all divided by n times the sum of the x squareds, that's the 55, minus the sum of the x's quantity squared. And you can see, if you can look close enough there, it does say a little 2.2 there. Yeah, that's 2.2. There's the slope. To emphasize, re-emphasize that formula again. Something else that's worth emphasizing here is that you can use this spreadsheet here that you see to figure out SSE. First, to figure out residuals. Oftentimes, when people try to apply the regression, they also graph the residuals. This is worth doing. What are the residuals that's worth reminding ourselves of? Residuals are the errors. The errors are the actual values minus approximate values, alphabetical order, actual before approximate. Actual values are the actual y data values. Approximate values come from the regression line. Use parentheses here, the slope, -1, or the intercept, -1, plus the slope times the x value, like this. That's going to be the first residual. Y is 2. What's y hat? That's really y hat, the second term in the parentheses there. Predicted value. Plug in 1 into the regression equation. We get -1 plus 2.2, 1.2. So we're going to do 2 minus 1.2 here, 0.8. Yeah, that first point was above the regression line. Remember the picture? That first point was above the regression line. This residual is positive. The next 3 residuals are negative, and the last one's positive. These residuals, by the way, do sum to 0. That's why we don't want to minimize the residuals themselves, because you always get 0 in the sum. So we don't bother summing those, but we can square the residuals, squared resids, like this. And then we can add those numbers up and get SSE. There's SSE. 2.8 is the minimum value of SSE when B0 is -1 and B1 is 2.2. SSE is minimized. If you used any other slope at any other intercept, used any other line, you'd get a bigger value of SSE. That's the minimum value of SSE for a line for these data points. I'll also tell you it's important when doing regression to use SSE to compute another quantity. It's called the regression standard error. Oops. Regression standard error. It's kind of analogous to a standard deviation, but not for a list of numbers. Instead, it's analogous to a standard deviation for the regression overall. What in the world does that mean? Let me just compute it. Its formula is square root of SSE divided by n minus 2. Not n minus 1, n minus 2. When you do single variable linear regression, there's a degrees of freedom involved, and it's n minus 2, not n minus 1. When you learn some multivariable linear regression, for example, if you had 2 independent variables, or if you were doing quadratic regression, the degrees of freedom is n minus 3. Or if you had 3 independent variables, or if you were doing cubic regression, the degrees of freedom is n minus 4, which means in that case, you better have more than 4 data points. Weird, weird, weird. And why would we care about this? And why would we care about degrees of freedom? Because this would be all related to doing inference in this context. What am I talking about? Let me show you now how to get some output that you should be able to read for the exam. It's kind of complicated looking output, but we'll limit what we look at in the output to a fairly small bit of it. Oh, let's see. What do I need here? Extensions. Why is that menu so small? There we go. Extensions, add-ons. I've got the add-on that I need there. It's XLMiner Analysis Toolpak. By the way, if you can't tell, I'm in Google Sheets here instead of Excel. If you didn't have that, which you probably don't, you'd want to get add-ons, and you'd want to search XLMiner Analysis Toolpak, okay? And you'd want to load it. Doesn't get the greatest rating compared to Logic Sheet and Power Formulas, but okay, it's what I'm used to using, so you should use it. XLMiner Analysis Toolpak. We're going to use it here. You probably want to practice this a little bit. Use it, start. There it is. There's a menu. There's a bunch of things you can do. We're after linear regression right there. First thing you should do, this is probably worth writing down or rewatching this video. My phone timer is at about 35 minutes. First thing you should do is click the labels box. Not that you have to, that's just what I recommend. However, if you do click the labels box, then when you, for example, choose the Y range, you want to make sure you include the label of the Y range, which is the Y in cell C1. The labels is supposed to be the variable names, X and Y in this case. In applications, you might want to use words for the labels, like X is number of hours of sleep and Y is how many problems you get right in the final exam. Sleep, problems correct or something. Actually, that's one of the sample problems in the video I'll share with you. Click the box, C1:C6 shows up. I could have just typed that. Highlight the X's, including the X label, and click the input X range B1 colon B6 shows up. I'm sorry, it's so small here. What else do we want to do? We also want to click the output range. We're about to get some output. And the output range, what goes in this box is going to be the upper left corner of the output. What cell does it go in? I want to make sure it just doesn't overlap with what I see here. So maybe I want to choose it to be cell G11. G11. And I'm not going to require this on the test, but as a default, I like including maybe residuals and residual plots as well. You could do other things. I think this is good enough to click OK. You do see a confidence level of 95%. That means there's going to be some confidence intervals that are 95% confidence intervals in this output. Click OK. And we got some output. A lot of output, including some residual plot. Yeah, 2 positive residuals, 3 negative ones. And the residuals themselves are down here somewhere. Yeah, there's the residuals. These are the same numbers I got before. Up further. And these are the y hats, the predicted y's, which I never actually computed in a separate column. What should you be able to read? You want to focus on the very bottom of the table. This part right in here. This number, -1, is labeled with the word intercept. Hey, yeah, that is the y-intercept. This 2.2 is labeled with the word slope. No, it's not. X. Okay, but that is the slope. Why is the word slope not there? Because if you were doing multiple regression with more than one variable, you'd have more than one quote-unquote slope. What do you want to label them all with the word slope? Now, this is the rate of change with respect to x. Might be a better way to say this. You also see, let's go over here. This is the next easiest thing to figure out. And I can never figure out why with this XLMiner regression analysis toolpak, why it redoes this stuff over here. It's like it redoes it. And it's been this way for the last 20 years that I've used this XLMiner toolpak. Like, why don't they fix that? Maybe that's why it's a lower rating. It's like, I don't need this part because it's just repeating it. What is this? That is the left and right endpoints of a confidence interval, a 95% confidence interval, to estimate not the sample slope, but the population slope. Wait, population slope? What's the population? Here's another instance where this application is phony. There would be no population slope for this example, whether you thought about all the prime numbers or just even the first 5 prime numbers. Okay, usually when you're thinking about estimating a population slope, you imagine you've got population data, not literally, it's just in your imagination, that has maybe millions and millions or billions and billions of data points. Of course, your sample size is much smaller, hundreds maybe. And that population data has a population regression line that you are just trying to estimate. What are the names of the population intercept and slope? They're not B's. They are betas. Beta 0 and beta 1. Oh, of course, Greek letters. Beta is the Greek version of B. By the way, on this page, which happens to be page 387, section 11.2, there are lots of typos on this page. Unfortunately, that's supposed to be a capital B0, capital B1. That's supposed to be a beta 1 there. Okay. Lots of typos on this page. Well, I guess at least 3 of them. This is good. Beta 0 plus beta 1 xi. That's effectively the formula for the equation of the population regression line. To keep in mind, though, beta 0 and beta 1 are parameters. You don't know what they are, right? They're population parameters. You'd be trying to estimate them. Assume they exist. Now try to estimate them. Based on some other assumptions, other model assumptions for simple linear regression when you were doing inference. Essentially, if you model the y values as random variables for different x's, you get a bunch of independent random variables that are all normally distributed. That the mean of yi is beta 0 plus, yes, that should be a beta 1 xi. And the variance of each y is sigma squared. What's sigma squared? Is just some number that you can estimate with, where is it? That number squared. Oh, and by the way, that number is the same as this number. Not an accident. Regression standard error. Its square would be an estimate for, in this model, this thing called sigma squared. We're talking about modeling the variation in the y values as x changes. The variance of each y stays constant, but the mean changes depending on what x is, because you got some line with some non-zero slope, possibly positive, possibly negative, telling you how the mean of y is changing. But y is normally distributed for any given x with this a certain mean depending on x and a certain fixed variance. That's the underground assumptions of the model. Why do we make these assumptions? So that we can actually do something. That's why. Are the assumptions always valid? No, they are not. They're not valid in the prime number example, but we're doing it just for fun. If we pretended our prime number example wasn't really about prime numbers, but was a random sample from some larger population for some other application, then we would be saying that this confidence interval is an estimate for the population slope. It's an interval estimator for the population slope. I'm 95% confident that the population slope is somewhere between those two numbers. I could also do hypothesis tests on the slope. What would such a hypothesis test look like? Whoops. Pretend that didn't happen. What would such a hypothesis test look like? Beta 1 equals 0 versus beta 1 is not 0 is the most common one to do. And in fact, in the spreadsheet output, that's the assumed test that you're doing. When I teach statistical analysis, this is the only hypothesis test that we do in regression. Not that you couldn't do others, but this is the most fundamental one to do, because essentially in testing this, you're testing whether the regression is significant or not. Is it statistically significant? Are you going to reject this null and say, yes, I do have a slope that's non-zero, as opposed to a slope that is 0, and why are you even doing regression? Because y doesn't depend on x. Why would you even do regression if the slope is 0? Or at least so close to 0 that you can't tell the difference. This is always, 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 for my classes at least, including this class, the only test that we do. Notice it's two-tailed, because we're just interested in whether the slope is 0 or not. And we're hoping, if we like to do regression, we're hoping to use regression, we're hoping to reject the null hypothesis here. Can we? There's the p-value, less than 1%. Yeah, I think I can reject the null. P-value is about half of 1%. Based on what? Based on this t statistic right there of 7.2. Where'd that come from? There's a formula for it. How many degrees of freedom lead you from that t-stat to that p-value? N minus 2. 3 degrees of freedom. N is 5 here. N minus 2. 5 minus 2 is 3. 3 degrees of freedom. Let's confirm that it worked here. Does that t-stat of 7.2, use inf correspond to a p-value. No, don't use inf correspond to a p-value of 0.005. Use distribution, use TCDF. TCDF, go up to 7.2, 3 degrees of freedom. When I paste this in, the area should be close to 0.995, right? If the area to the right is going to be 0.005. Well, okay, it's off a bit. Oh, that's because I forgot. That's the one-tailed p-value times 2 for the two-tailed. There we go. It's doing a two-tailed test by default. The p-values that you see in this output are always two-tailed p-values. Double the one-tailed p-value. They're not the exact same when you compare, because I used 7.2 instead of 7.20119038. What's the standard error? Essentially, it's an estimate from the sample for the standard deviation of the sampling distribution of B1. As a statistic, I would suggest doing the reading in section 11.2 to understand the big ideas, even if you don't understand all the formulas. At least read the beginning of it. B2, or not B2, what am I saying? B1, capital B1 is our symbol for an estimator of beta 1. It's a statistic, a random variable computed from a sample. Is it unbiased? Yes. The expected value of capital B1 is beta 1. The mean of the slope is the slope. The mean expected value of the slope random variable as an abstract quantity is the population slope when I'm assuming I'm doing random sampling. Is that proved in the book? Yes, it is. Is it worth studying the proof? Only if you're a glutton for punishment. Where is it done? Oh, it's done on pages 389. Okay, the derivation starts here. Here's the formula for capital B1. Notice it involves a capital Y. It is a random variable because capital Y is a random variable. The X's are all lowercase. You assume you're given the X's. And then they write it like that. And then they say, hey, it's really a linear combination. And so by rules for expected value, you can write this, blah, 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 blah. It goes on to the next page. Blah, 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 substituting, blah, 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 blah. There you go. There's the conclusion. Next thing to do, variance of B1. Oh, blah, 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 blah. There's the variance of B1. What in the world? Yeah. Sigma squareds that assumed population variance for the yi's, no matter what x is, and that's SSXX, our friend from Tuesday. SSXX. Leading to this conclusion, ultimately, and B1 is also normal, by the way. B1 as a statistic is normally distributed with mean beta 1 and this variance, and you'd have to take the square root of that thing to get the standard deviation then. And that's the basis for doing the inference. Getting the confidence intervals and doing the hypothesis testing. Though because we're using a sample, we have to worry about degrees of freedom, and we have to convert to a t statistic and use n-2 degrees of freedom. This formula here is an estimator for sigma squared. That's what we did in the spreadsheet right there. SSE divided by n-2. Remember doing that? I made the column for SSE. I added those the squared residuals up. Then I divided by n-2. Then I took the square root to get an observed value of S. an estimator for the regression standard error. S squared, the squared regression standard error, maybe regression standard variance, I don't know if that's its name, is an unbiased estimator for sigma squared. Oh yeah, there's more crazy formulas in this section, blah, 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 blah. Blah, 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 blah. It's overwhelming. Then a new section, 11.3 and 11.4 wouldn't be bad to read. They're a little easier. In 11.3, you do see the formula for the t-statistic for testing the test that we did. T n minus 2 degrees of freedom is B1 divided by this thing, S over square root of that SXX is what I called SSXX. That fraction in the bottom of this bigger fraction is an estimate for the, it's called the standard error for the slope. It's an estimate for the standard deviation of the sampling distribution of B1. It's estimated in this case by that number right there.